On this worksheet, we're going to solve a couple of different problems involving radioactive decay. Radioactive decay follows first-order kinetics, which means for a substance that's undergoing radioactive decay, the half-life of that substance is equal to 0.693 divided by the rate constant, K. Also, for radioactive decay, we know that we can use the instantaneous rate law for first-order reaction. So we know that the natural log of the concentration of substance at time t is equal to negative kT plus the natural log of that substance at time 0. And for radioactive decay, for nuclear areas of nuclear chemistry and radioactive decay and things like that, chemists actually take this equation and they rearrange it a little bit and change the terms up a little bit. So the form of it that you'll see used looks like this. The natural log of n sub 1 over n sub 0 equals negative kT. And it might initially look like it's a totally different equation, but all that's happened is the natural log of a at time 0 has been moved over to the left-hand side, so that's going to give us this form right here. And then instead of saying a at time t and a at time 0, they say n sub 1 and n sub 0. There are actually a lot of different things that we can plug into this equation. It does not have to be molarities. It could be the number of objects, which should make sense to you because molarity is moles, which is, a way of counting number of objects. So you'll see a number of different things. One thing that is kind of strange to me is that I'm not sure why this is not an n sub t. That would be really consistent with this notation here, but whatever. Also want to point out that there are a couple of typos on this worksheet. So one right here in the first problem, it says that the half-life of carbon-14 is 1.21 times 10 to the minus 4 inverse years. That's actually K. That's actually rate constant for carbon-14, not the half-life. There's another typo on the last problem, which I'm going to correct right now before I completely forget to do it. Again, it's this same problem. The rate constant is 4.51 times 10 to the minus 4 inverse years. Okay, so let's take a look at these problems. The first problem is asking us, what is the carbon-14 activity in disintegrations per second? This is a lot of times abbreviated DPS for a piece of wood that is 23,000 years old. Disintegrations per second is one of the things that can be plugged into this equation in place of n sub 1 or n sub 0. So this problem is asking us to calculate the disintegrations per second for something that is 23,000 years old. That's going to be our n sub 1. That's going to be the n at time equals 23,000 years. So this is our time, 23,000 years. Fresh cut wood, so that's going to be wood that hasn't started disintegrating that yet. It has an n sub 0 of 15.2 disintegrations per second. And then also, obviously, we know the K. So for this problem, the equation that we're going to be using is right here. We know the n sub 0, we know the K, and we know the T. So we can go ahead and plug these things into this equation. The natural log of n sub 1, which we don't know, over n sub 0, which is 15.2. That's equal to the rate constant, 1.21 times 10 to the minus 4. Units are inverse years, times the time, 23,000 years. And then we just have to solve this problem. To solve this problem, we've got to get rid of the natural log. So we'll take the natural log away from the left-hand side, and the right-hand side is going to be e2, that whole term, 1.21 times 10 to the minus 4th. I'm going to get rid of the units since they cancel each other out, times 23,000. I'm going to solve this much of it for starters. Negative 1.21 times 10 to the negative 4th times 23,000. E2 that number. See, I got, just so we can keep track, I got e to the negative 2.783, and that worked out to be 0.06185. And so now I'm going to write the left-hand side again. I have n sub 1 over 15.2 equals my right-hand side, which I've done all the math on, works out to be 0.06185. So n sub 1 is 0.940, and the units of that are disintegrations per second. This is just saying the number of times that the substance disintegrates every second. Okay, so for our next question, this is telling us that we have iron 59 and it is decaying to cobalt via a beta emission process. It has a half-life of 45.1 days. So let's make a note of that. The half-life is 45.1. The unit is day. Write a balanced nuclear reaction for this process. So we've got iron 59 and it is undergoing beta emission. So that means that it is losing a beta particle, otherwise known as an electron, and it is producing cobalt. And we need to figure out what these numbers are right here. Easiest way to do that is to go look at a periodic table. Let's pull one up. Here is iron. Iron's atomic number is 26, so we'll fit that right there. Cobalt's atomic number is 27. Those numbers always come from the periodic table. And then for the mass number, we're going to calculate that. 59 on the left-hand side, which means our total mass on the right-hand side needs to be 59 as well. There's our balanced equation. We've got that done. Now we need to calculate the rate constant for the decay of iron 59 to cobalt. We've got to figure out what the rate constant is. So we could do that using the half-life equation because we know the half-life. So all we have to do is use this to solve for K. I'm just going to copy the half-life equation down here so we have it handy. Half-life is 0.693 over K. And again, the reason that I'm picking this equation is because it's asking me to solve for K. It's giving me this information, giving me the half-life. So this is the simplest way to do that calculation. I'm going to rearrange this a little bit. T1/2 times K is 0.693, and we're trying to solve for K. So the rate constant K is going to be 0.693 divided by the half-life. Let's plug in our half-life, 0.693 divided by 45.1 days. 0.693 divided by 45.1 is 0.0154. The unit is inverse day. Last part of this question, so we just calculated the rate constant. Last part, how many half-lives will elapse as 100% decays to 14.29%. This would be a really easy problem to solve if this worked out to be like a whole half-life number. Like, so if we started with 100%, after the first half-life, we go down to 50. After the second half-life, we go down to 25. I can't divide by 2. And then we go down to 12.5. And so this 14.29 happens somewhere in between this would be the first half-life, this would be the second half-life, this is the third half-life. So the 14.9 happens somewhere in between the second and the third half-life. We can't calculate it just straightforward like that. So what we're going to need to do is figure out, we can't like directly figure out how many half-lives it is. We're going to have to start by figuring out how much time, just in general, how many days are going to elapse as this sample decays. This is another example of sort of random stuff that we can plug into this equation right here. So in this n sub 1 and n sub 0 number, we can actually calculate or plug in these percentages in this place right here. For this problem, our initial amount, which we're going to be using as our n sub 0, and our initial amount is 100%. And at the time that we're interested in, the amount is 14.29%. So that's going to be our n sub 0 and our n sub 1. Let's get this equation set up for us. Then we're going to be using the natural log of n sub 1 over n sub 0. That's equal to negative kt. And again, we know the n sub 1, we know the n sub 0, we just figured out k, and so we're going to use this to figure out the number of days, how many days elapse. The natural log of n sub 1, so that's going to be n at the time that we're interested in, divided by the initial n, 100%. That's equal to negative our rate constant, 0.0154, the units are inverse days, times the time, which is what we don't know. Let's solve the left-hand side first. The natural log of 0.1429 is negative 1.946. The right-hand side is negative 0.0154 days to the negative 1 times the time. We can solve for the time. Time is the negative 1.946 divided by negative 0.0154. That is 126, and the unit is day. That's not what the problem is asking us to solve. The problem didn't ask us how many days is it. The problem asked us how many half-lives is it. Every half-life is 1 day. To solve this, we're just going to do like a unit conversion problem. We're going to say we know it's 126 days. We know that 1 half-life, I'm just going to use our abbreviation T1/2, 1 half-life is 45.1 days. So if we set it up like this, that day unit is going to cancel, and we're going to be left with the number of half-lives. So we're basically just dividing the number of days by the length of our half-life, 2.8 half-lives. Okay, for our last problem. This problem is telling us we have a rock. The rock is made up of uranium-238 and lead-206, so it has both of these substances in it. Uranium-236 undergoes decay to form a lead-206. So the assumption here is that the rock was originally all uranium, and then the uranium started to undergo decay, and the uranium was converted to lead. At this particular time, some of the uranium has decayed and turned into lead, but not all of it. And we've been given the rate constant for the decay. Actually, looking at, remember I told you that I thought that this was a mistake. Originally I said it was the half-life. Looking at the wording of this problem, I think that I misinterpreted the mistake. The half-life is, no, that doesn't make sense. This has to be K. Has to be K. Okay. So the first thing that it wants us to do is refer to a figure in the textbook to determine the stoichiometric relationship between uranium and lead. And so if you have your book handy and you can take a look at that uranium radioactive decay series, that's handy. If not, I'll just tell you the uranium-238 undergoes a series of radioactive decay steps, and ultimately it produces lead-206. So this, what I've written here, is not a balanced equation. That's what the multiple arrows represents. This is just saying that if I have 1 uranium-238, it's going to be converted into 1 lead-206. The stoichiometric relationship between these two substances is 1:1. So that's the first part of the problem done. Now, what's going on in this situation is that we have a rock that currently has 4.31 milligrams of this uranium, and it has 2.47 milligrams of the lead. The rock originally was all uranium. Some of the uranium has decayed and turned into lead, but not all of it. So at this particular moment, there's 4.31 milligrams remaining, hasn't decayed yet, and we've got 2.47 milligrams of lead that has been produced. So the next question that we're going to answer, determine the mass of uranium-238 that must decay to produce 2.47 milligrams of lead. What we want to try to figure out is how much uranium has already undergone decay and turned into this lead. And we're going to do that with just a gram-to-gram conversion. We know that we have 2.47 milligrams of lead, and we want to convert that into grams. There are 1,000 milligrams in a gram, and then we want to convert our grams of lead into moles of lead, because the only way we can relate lead to uranium or any atom to any other atom is a mole-to-mole ratio from a balanced equation. So we need to know how many moles we have so that we can convert our moles of lead into our moles of uranium. Now, one of the nice things about this problem is that the mass number is written on there for us, and the mass number is the atomic mass, so we don't have to look it up on the periodic table. The balanced equation tells us it's a 1-to-1 relationship. Now we can start converting our moles of uranium into milligrams. First, we're going to convert the moles of uranium into grams using its mass number, 238 grams per mole, and then we can convert that into milligrams. 1 gram is 1,000 milligrams, and this is going to be the milligrams of uranium-238. And again, what we're calculating here is, it's easy to lose track of what we're actually doing. What we're calculating here is how much uranium has already decayed to turn into that lead-206. 2.85 milligrams. So again, this is 2.85 milligrams of the uranium-238, which has already decayed. And then we have 4.31 left over. So that, we just answered this question right here. Second part, determine the original mass of uranium-238, the original mass. So to get the original mass, we're going to take what we currently have left over. We currently have 4.31 milligrams. We know that we just calculated that 2.58 milligrams of it has undergone decay. So that's going to give us our original mass. 7.16 milligrams was our original mass of 238 uranium. This is what we have currently, and this is what we have already decayed. Determine the rate constant. Like I said, I'm a little confused about exactly what kind of typo I made here. I think the rate constant is given to us right here. This number here has to either be the rate constant or the half-life, and that's a really small half-life. So I think that this is the rate constant. So I don't think we need to determine the rate constant. I think it's right there. The last thing that this is asking us to do is calculate the age of the rock. I suppose when we plug these numbers in, the age of the rock is going to kind of give us a hint about whether or not I have correctly calculated my typo. So to calculate the age of the rock, we're going to be using this equation right here. So we're using this equation in terms of uranium because we're trying to figure out all of this. So we have the K value for uranium. So our current amount, N sub 1, our current amount of the uranium is right here. And our original amount of uranium is, boom, right there. And then our K is the 4.51 times 10 to the minus 4 right there. So we're going to go our current amount, 4.31, divided by our starting amount, 7.16. That's going to be equal to negative K 4.51 times 10 to the minus 4 years inverse times the time. I'm excited and a little bit nervous to see what we get here. So the left-hand side is negative 0.5076. That's equal to negative 4.51 times 10 to the minus 4 years times the time. And these rocks, they should be really old, so this should be a really big number. Negative 5.076 divided by negative 4.51 times 10 to the minus 4. Time is 1,125 years. So that definitely seems like a reasonable answer.